Hello everyone, I am Pawan Kumar Sak, PhD scholar from IIT Kanpur. I am the TA for the course Elements of Solar Energy Conversion, and this is the 10th discussion hour for this course. So till now we have solved some problems based on the relations between different angles. After that we have solved some problems on the part shading. After that I have solved some problems on flat plate collector, and in the last week we have covered the problems based on the parabolic trough collector and the compound parabolic trough collector. Okay, so today we will see some problem based on the photovoltaic conversion. So today we will see some problems on this topic, like theoretical and some numerical problems. So let's move to the first problem. The first problem is that discuss the intrinsic and extrinsic semiconductor with the Venn diagram. So first I will discuss the intrinsic semiconductor. So intrinsic semiconductor mean that a pure semiconductor in which the electron and hole concentration are equal. Okay, and in this definition, the pure mean there will be no impurity. So first let me draw a Venn diagram. So suppose this one is our valence band and this one is our conduction band. And in between there will be Fermi level. So what will happen in the intrinsic semiconductor, that the number of holes and number of electrons will be equal. So suppose there are some holes in the valence band, then equal number of electrons will be available in the conduction band, and these electrons will contribute in the current flow. So here if there will be some impurity, then what will happen, that there will be some deficit of electrons or maybe some deficit of holes may be present. So I am writing that because of the impurity in the crystal, electron or hole may be captured. Okay, so in the intrinsic semiconductor, the number of electrons that we will represent by n will be equal to the number of holes, that will be p, and we can write it is equal to the Ni, that is intrinsic concentration of electrons and holes. So now let's move to the extrinsic semiconductor. So in this extrinsic semiconductor, there may be two types. first one, that if there are more number of electrons, then it is called the n-type semiconductor. And if there are more number of holes, then it is called p-type semiconductor. So first I will discuss the n-type semiconductor. So in n-type semiconductor, what happened, that suppose these are our valence band and this one is our conduction band, and in between there are the Fermi level. Then initially what will happen, that there are equal number of holes and electrons. Now what will happen, that because of this, generally we do this extrinsic semiconductor by the doping. Okay, so doping mean we add some external material that have the extra number of electrons or maybe extra number of holes may be happen. So in n-type semiconductors, generally we dope with the fifth column elements, and those are like phosphorus, arsenate and Sb. Okay, so in these metals there are more number of electrons, and because of this more number of electron, what will happen, that this Fermi level for this n-type semiconductors moves upward. So there will be an additional, or sorry, this will be the Fermi level for the n-type semiconductor, and this extra electrons that can move to the conduction band easily. So these are the extra electrons because of this doping. So these were the original or intrinsic electrons, and this will be the extrinsic or external electrons due to the doping. Okay, so in this case what will happen, that the number of electrons that we have defined as n will be greater than the number of holes. So now next we will move to the p-type semiconductor. So in p-type semiconductor there will be more number of holes, and we will do this by adding some doping from the column element of column third, such as boron, aluminium, gallium and indium. So what will happen with the band? So suppose this one was the valence band, this one was the conduction band, then the Fermi level will shift towards the valence band because of the increased number of holes. Holes is not a different atom, it is just to represent the deficit of the electron. So this one is the acceptor band, EFP. Okay, so if there were initially few number of holes and the equal number of electrons, then because of the doping there will be increased number of holes. So these are the holes because of the doping. Okay, and because of the doping what will happen, that the number of holes that we represent by P will be greater than the number of electrons, that is n. Okay, so that's all in the question have been asked, that define the intrinsic and extrinsic semiconductor. Okay, now next move to the next problem. So in the second problem, it has been asked that show an energy band diagram for an n-type semiconductor in real space. In this diagram, identify the conduction band age, valence band age, and electron affinity, work function, vacuum level, intrinsic Fermi energy level, band gap energy, and the Fermi energy level. Okay. So first let me draw the band diagram. So this one will be the valence band, and this one will be the conduction band, and in between there will be intrinsic Fermi level EI. Let me denote it as EGI. EFI. F for the Fermi level. Now, so in this band diagram, you can consider that the energy for the valence band is near to this edge of this band, valence band. That's why I am writing this EV at the edge of this band. Similarly, for the conduction band, the energy level can be denoted near to this edge, that is represented by the EC. And now what will happen, that because of the doping, and in the problem it is given that it is n-type semiconductor, so the Fermi level will shift towards the near to this conduction band. So this one will be the Fermi level for this n-type. Okay. Now we have to see that I have represented the conduction band is and the valence band is. Next one is the electron affinity. So before coming to the electron affinity, first we have to see that there is one level called the vacuum level. So this one is the vacuum level, and the vacuum level is defined as, so it is defined it defines the energy level where the electron is just free from the solid. Okay, so this is the maximum energy, and it defined as the vacuum level. Okay, so now I can represent the electron affinity. So electron affinity, let me first write the definition for this. And it is defined as the symbol chi. Okay, so it is the minimum energy required to remove an electron from the semiconductor. Okay, so what will happen in the semiconductor, that there will be, sorry for the inconvenience. Okay, so I was saying that there will be holes in the valence band and there will be some electrons in the conduction band. So the minimum energy mean that you can remove the electron from the conduction band. So the electron affinity is defined as the minimum energy that will require to remove the electron from the semiconductor. So this is the minimum energy that will require to remove, and it is denoted by the symbol chi. Okay, now the next is the work function. So work function is the, let me write the definition for this. It is denoted by the phi. Okay, so this is the energy required to remove an electron from the Fermi level. Although as we know that in the Fermi level there will not be any electron, but this is the an theoretical definition for this work function, and it can be seen from the figure that if this is the Fermi level for this n-type semiconductor, then the energy required to remove the electron from the Fermi level will be this much. So and this one is defined as the phi symbol. Okay, so in the problem, next one is the vacuum level that I have defined. Next, intrinsic Fermi energy level, that this one, EFN. Next is the band gap energy. Okay, so band gap energy is the difference between the edge energy of this valence band and the conduction band, and it is denoted as the EG. Next is the Fermi energy level that I have defined as the EFI. Okay, sorry, EFN for the n-type semiconductor. EFI is the Fermi level for the intrinsic semiconductor. Okay, so that's all in the question have been asked. Now next move to the next problem. So this one is the numerical problem, and in the problem it has been asked that calculate the probability of finding an electron at an energy level of 8 electron volt. Given that the Fermi energy is the 20 electron volt and the temperature is given as 300 Kelvin. So as we know the Fermi function that is defined as Fe is equal to 1 upon 1 plus e to the power e minus ef divided by the kT, where k is the Boltzmann constant. And the value for the k is 8.62 into 10 to the power minus 2 in electron volt per Kelvin. Or if we want to write it in joule, then it is equal to the 1.38 into 10 to the power minus 23 joule per Kelvin. Okay, so in the problem it has been asked that we have to find the probability for the electron at an energy level of 8 electron volt. So in this problem the E is given as the 8 electron volt, and the Fermi energy level, that is EF, is given as the 20 electron volt. The temperature is given as 300 Kelvin. So now with this formula we can calculate the probability of an electron in the energy level of 8 electron volt. So this Fe will be 1 divided by 1 plus e to the power bracket 8 electron volt, that is E, subtracted by the EF, that is 20 electron volt, and divided by the K. Now you can see that these E and EF is in electron volt. So we should write the formula of K in terms, the value of K in terms of electron volt per Kelvin. So that is 8.62 into 10 to the power minus 2, and this one is multiplied by the temperature that is given in the problem as 300 Kelvin. So now if we will try to solve this, then this term will come out as 0.6287, and when you will solve, then this Fe will come out at 0.61. So this 0.61 means that if we are trying to find the probability for an electron in this energy level, that is 8 electron volt, then the value is 0.61. Okay, so now let's move to the next problem. So in the next problem it has been asked that given that the densities of states related effective masses of electrons and holes in silicon semiconductor are approximately 1.08 ME and 0.60 ME respectively, and the electron and the hole drift mobilities at room temperature are 1400 and 450 centimeter square per volt per second respectively. Calculate the intrinsic concentration and the intrinsic resistivity of the silicon. Okay, so in the problem, this effective masses that we have represented as ME star for the electron is given as 1.08 ME, where ME is the mass of electron, and it is equal to the 9.1 into 10 to the power minus 31 kg. Okay, next the Mn star, that is the effective mass for the hole, is given at 0.60 ME. Okay, so if we will try to find the effective density of states, then for the conduction band the NC will be equal to the 2 in the bracket 2 pi ME star KT divided by the H square ka whole power 3 by 2. So in this formula we have all the values and we can put. So this NC will be equal to the 2 multiplied by the 2 pi into ME star, that is given as 1.08 ME. So it will be 1.08, and from the ME value is 9.1 into 10 to the power minus 31. Okay. Next, it is multiplied by the K. So it will be 1.38 into 10 to the power minus 23 multiplied by the temperature, that is 300 Kelvin. It has been taken as the room temperature, and the H value is 6.63 into 10 to the power minus 34 the whole square, and the whole term is powered by the 3 by 2. Okay, so when you will solve, then you will find that this NC value comes out to be 2.81 into 10 to the power 25 in per meter cube. Okay, now if we can try to convert it in per centimeter cube, then this value comes out to be 2.81 into 10 to the power 19 centimeter per centimeter cube. Okay, similarly we can find the value for this NV, and the formula is given as 2 multiplied by the 2 pi. Instead of this ME star, now the term that is will come as the Mn star, the effective mass of the hole, and it is multiplied by the KT divided by the H square, and the whole power is 3 by 2. Now in this formula also we have all the value, so we will put these values. Mn star is given in the problem at 0.60 ME, so it will be 0.6, and this multiplied by the ME, that is the weight of the electron, so it is 9.1 into 10 to the power minus 31. After that, the value for the K is 1.38 into 10 to the power minus 23 joule per Kelvin, and multiplied by the temperature, that is 300, and it will be divided by the H square, that is 6.63 into 10 to the power minus 34 the whole square, and the whole term will be powered by the 3 by 2. So when you will solve this, you will find that this value comes out to be 1.16 into 10 to the power 25 per meter cube. Similarly, as we have convert this into per centimeter cube, then it will come out to be 1.16 into 10 to the power 19 per centimeter cube. Okay, now Now we have both the values, that is NC and NV. Now we can use the formula for this Ni, that is Ni is equal to the NC NV की power half exponential of minus Eg divided by the 2 kT. Okay, so Eg, we will use the general value for this Eg for this silicon semiconductor. So NC we have calculated it as 2.81 into 10 to the power 19, and this NV value is 1.16 into 10 to the power 19. So I am taking the values in terms of per centimeter cube. So this Ni value, that is the concentration, it will also come out in number of holes or electrons per centimeter cube. So this whole term is power by half, and in the exponentially it will be minus Eg. So the Eg value is 1.10 electron volt, and this K value that I am writing as 8.62 into 10 to the power minus 5. This will be in electron volt per Kelvin, and then I will write the value for this temperature, that is 300 Kelvin. So in the bracket term, all the units will be cancelled out, and this will come out as number. So this Ni will come out as 1 into 10 to the power 10 per centimeter cube. That has been asked in the problem. So calculate the intrinsic concentration, that is Ni. Next in the problem, it has been asked that we have to compute the intrinsic resistivity of the silicon. So as we know that the resistivity that is represented by this rho, it is inverse of the conductivity, so that is represented by the sigma. So if we are able to find the value for this conductivity, then we can calculate the value for the resistivity. So for the semiconductor, we can compute the conductivity, that is sigma, as equal to the total conductivity for the electron plus conductivity for the hole, that is represented by the E and mu E, where mu E is the mobility, and it is given in the problem also. So that is given as the 1400 for the electron and 450 for the hole constant for the hole. Okay, so this one is the drift mobility. Okay, and this one is for the hole. Okay, so as we have the value for this N and P, and in the intrinsic semiconductor, the value for the N is equal to the P, and it will be equal to the Ni for the intrinsic semiconductor. So now we can put the value. Also we can take this. We can replace this N and P by the Ni. So this sigma will be equal to the sigma Ni mu E plus E Ni mu N, and then we can take this Ni common. Then in the bracket there will be the addition of this drift velocity for the drift mobility for the electron and for the hole. So now if we put the value for the E is 1.6 into 10 to the power minus 19 coulomb multiplied by the Ni that we have calculated as 1 into 10 to the power 10 centimeter per centimeter cube, and the value for the mu E is given as the 1400, and for this mu N it is given as the 450. Okay, so now if we will solve this, then we will find that this sigma is come out as 3 into 10 to the power minus 6 ohm inverse centimeter inverse, and after calculating this conductivity, we can find the resistivity as equal to the 1 by sigma, that will be 1 divided by the 3 into 10 to the power minus 6, and it will come out as 3.3 into 10 to the power 5 ohm centimeter. Okay, so this is the answer. Okay, so these two things have been asked in the problem that we have solved. Now we will move to the next problem. So in the next problem, it has been asked that for intrinsic carrier concentration for silicon at room temperature, that is at room temperature, the intrinsic carrier concentration is given, that is 1.5 into 10 to the power 10 centimeter per centimeter cube. So there are three parts for this question. In the first part, it had been given that if it is doped with 1 into 10 to the power 16, this one is the P that represents the phosphorus atoms per centimeter cube, and all the dopant atoms ionized at room temperature. Find out the shift, both magnitude and direction, with Fermi level with respect to the intrinsic value. Okay. In the next part, we have to calculate the whole concentration, that is doped silicon, as in the previous part, that is one. In the next part, it has been given that this semiconductor is doped with this number of this Al represents the aluminium material, aluminium atoms per centimeter cube, and only in this problem it has been given that the only 50% of the dopant atom ionized at room temperature. So we have to calculate the minority carrier concentration. So now first we will solve the first part. So first, in the problem, the intrinsic carrier concentration that we represent as the Ni is given as 1.5 into 10 to the power 10 centimeter cube. Now we will move to the first part. So in the first part, it is doped by the phosphorus atom. So as I have discussed in the first problem, that if we doped with this phosphorus that belongs to the column 5, then what will happen, that there will be more number of electrons, and it is called as the n-type semiconductor. Okay, so in the problem, the doped number of atoms is given as 1 into 10 to the power 16, and it has been given in the problem that all the dopant atoms ionized. It means that what we are doping, all are contributing to this ionization. So this donor concentration is given as 1 into 10 to the power 16 atoms per centimeter cube, and as I have discussed that this phosphorus um, um, belongs to this column 5, and because of this doping of phosphorus, there will be more number of electrons. So this doping, this value and Nd, that will be equal to the number of it will be equal to the concentration of the electron that we have denoted as NO. Okay, so if we have the value for this NO, that is 1 into 10 to the power 16 atoms per centimeter cube, then we can calculate the uh, difference between the find out the, then we can calculate the shift between the Fermi level. Okay, so first let me write the formula that you have seen in the lecture notes, that is given as n naught is equal to the Ni e to the power Ef minus Ei divided by this Kt, where Ni is the concentration for the intrinsic semiconductor, and n naught is the concentration of electrons because of the after the doping, and this Ef minus Ei is the shift that is asked in the problem. So this we have to calculate. So if we will put the values for this n naught or Ni, or we can take the log, that is n naught divided by Ni, then it will be equal to the EF subtracted by the EI divided by the KT. Then the shift, that is EF minus EI, it will be equal to the KT ln N naught divided by the Ni. Okay, so now we can put the values for this K and T and N naught and Ni. So this K value is 8.62 into 10 to the power minus 5 electron volt per Kelvin, and this temperature value will be 298, and in the Ln the value for the N naught is given as 1 into 10 to the power 16, and it will be divided by the Ni, that is 1.5 into 10 to the power 10. So when you will solve this, you will find that this value comes out to be 0.355 electron volt, this EF minus EI. So from this data we can see that the value comes out in positive. What does this mean? That the EF, that is the Fermi level after the after the doping of this phosphorus atoms, is greater than this EI. Okay, so it means it will shift towards the conduction band. So if we will try to draw the band diagram, then from the band diagram we can see that if this one is the valence band and this one is the conduction band, then this will be the energy for this valence band and this will be the for the conduction band. So this is the intrinsic Fermi level, that is noted as EI. It will shift towards the upward. Okay, so this one is the EF for the N-type semiconductor, and the shift will be this EF minus EI, and it is equal to the 0.355 electron volt that has been asked in the problem. Okay, so now move to the next part. So in the next part it has been asked that we have to calculate the whole concentration in the doped Si sample as mentioned in part 1, whole concentration. So now as we know that the multiplication of the concentration of this hole and the for the electron remains constant, that is equal to the Ni square. So now we have the value for this N naught. From here, from this formula we can calculate the value for this number of for the value of the whole concentration, that is P naught, and it will be equal to the Ni square divided by the N naught. And when we will put the value, so Ni is given as 1.5 into 10 to the power 10 a whole square divided by this N naught, that is given as 1 into 10 to the power 16. So when we will solve this P naught comes out to be 2.25 into 10 to the power 4 moles per centimeter cube. Okay, so from here till now we can see that after the doping we have calculated the concentration for the holes and the concentration for the electron, that is denoted by the N naught and P naught. Now we will move to the next part. So in the next part it has been given that this silicon semiconductor is doped with 2 into 10 to the power 15 aluminum atoms per centimeter cube, and only 50%. Okay, so as I have discussed that this aluminum material, it belongs to the column third, and because of this doping there will be more number of holes. Okay, but now in this time it has been given that only 50% of the dopant atoms ionized. It means that the whole concentration that we have denoted as P naught will be equal to the only 50% of the addition, that will be equal to the 0.5. So this one is for 50% multiplied by the total number of atoms added. and it is given as 2 into 10 to the power 15. 2 into 10 to the power 15. So this whole concentration will be equal to this 1 into 10 to the power 15 atoms per centimeter cube. Okay. Now, in the problem, it has been asked that we have to calculate the minority carrier concentration. Okay. So as I have told you that because of this aluminum doping, this will be the that I have not written. So it will be the because of this addition p-type semiconductor. So in this p-type semiconductor, what will happen that there will be more number of holes, and because of this more number of holes, the majority charge carriers will be the holes. Okay, and the minority charge carrier, those will be the electron. So we have to calculate the electron concentration, that is noted as N0. And as I have solved in the second part, that this multiplication of this N0 and P0 remains constant, and it will be equal to this and concentration of the intrinsic power chi square. Okay, so from here we can calculate the N0, and this will be equal to the 1.5 into 10 to the power 10 whole square divided by this 1 into 10 to the power 15. So this N0 will come out as 1.5 into 10 to the power 5 electron atom per centimeter cube. So this has been asked in the problem. Now, as in the first part, we have to find out the shift between the for the Fermi level energy level. Okay, so although it has been not asked in this problem, but we can compute the shift for this doping of the aluminum doping semiconductor. So the formula for this will be like P0 is equal to the Pi e to the power Ei minus Ef power k by divided by the kt. So we have the value for this P0, or we can simplify this formula as Ei minus Ef. This will be equal to the kt multiplied by the ln P0 by Pi. So if we will put the value into 298, this ln P0 that we have calculated as 1 into 10 to the power 15 divided by the 1.5 into 10 to the power 10. So when you will solve this, you will find that this value comes out to be 0.285 electron volt. So from the Venn diagram, we can denote it. Suppose this one is the valence band, this one is conduction band, and this one is the Fermi level for this intrinsic semiconductor. So because of the doping of this aluminum, the Fermi level will shift towards the valence band. So this will be the EF for the aluminum doping, that is for the p-type semiconductor. So and this is the shift that we have calculated as Ei minus Ef. Okay, so that's all the questions that I want to solve, and if you have any doubt, then you can mail me on this mail ID. Okay, so that's all for today, and thank you for listening.